Good morning to one and all present here. On behalf of PG and Research Department of Mathematics, DG Vaishnav College, I welcome all the CSIR aspirants. Prayer is talking to God Almighty, the creator of whole universe. So let's begin our session with the presence of God prayer.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिः सतां दर्शनेस्तु भवत्तनूनाम् नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनामविभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
This is C4 workshop. C4 means chase, crack, conquer, CSIR net, which will make the CSIR aspirants to go to the next level. Today, our resource person, Dr. N. Sridharan, retired professor and head, Department of Mathematics, Alagappa University, Karaikudi. Now, I handed over the session to you, sir.
Thank you very much. I'm happy to join this C4 group. I have selected one more C, complex analysis. Okay. I'll start from Cauchy's theorem and consequence of Cauchy's theorem to do some problems today. இது எடுத்து கொடுப்போம் அந்த இதே போட்டிருக்கேன் பவர் பாயிண்ட் பிபிடி ரைட் ஓகே ஹலோ I'll start with the Taylor's theorem. It states that if f of z is analytic in the domain D and a closed disk mod z minus a less than equal to r is contained in D, then there is a unique representation for f of z in this disk. That representation is represented by a power series a0 plus a1 z minus a plus dot 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 plus an z minus a power n. This is valid for all z in z minus a. Okay. Now consider this. என்னப்பா பண்ணோம் எழுதணும்
எழுதணுமா
வர மாட்டேங்குது
டைப் பண்ணுங்க
இல்ல படம் போடணும்
ஆனா வந்து இது ஒரு
இங்க வச்சுக்கணும்
இல்ல 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 அங்க இல்ல ஒயிட் போர்டு வேணா கொண்டு வரணுமா
இல்ல இங்க வச்சுக்கணும் கன்சிடர் திஸ் இருக்கு ஓகே
இல்ல இதுக்கு வந்து அது தேவைப்படாது
இது தேவைப்படாது
இது தேவைப்படாது
இது போணும்பா அப்பா கிட்ட just 1 minute please just 1 minute
இல்ல இல்ல நான் ஒயிட் போர்ட் போடுறேன் ஒயிட் போர்ட்
போடு இல்லையா போகணும் அப்போ
இதுல வர
எவரி வருது வரலையே
ஒரு நிமிஷம் லோட்
வரலையே வந்து முன்னாடி அப்பா பக்கத்தில் வந்தது
ஒரு நிமிஷம் லோட்
அப்பா கூப்பிட்டு போடனா வரல சார் ஏன் படி
ஒயிட் போர்ட்
ஒயிட் போர்ட் வேண்டாம் அதுலேயே நான் போட்டேன் இதில் தான் போடணும் நான் டெலிட்டு ஓகே ஆரம்பிச்சாச்சு இதை வைக்கணுமா யாரு சக்சஸ் ஓகே ஓகே D be the domain அங்க பாயிண்ட் போடுமா D be the domain and f is a function f is analytic function over this there is a point a is a point and you can consider a small circular disk around this and for every z on this point and this is a point a is it clear sir is it clear hello is it clear
voice is clear
this voice is very clear
Yes sir, yes sir.
Is it clear? Okay now in
Yes,
this small disk we can represent f of z as the power series a0 plus etc and this is valid only for all z in this circular disk but not any point here. If z is here the power series is not useful there. With respect to a this is valid only for the largest circular disk. It is not valid outside this. That is a theorem. Okay. Coming to this once again, f of z is given by that. If you substitute z equal to a, all the terms are 0 on the right hand side except a0. So f of a is a0. What is the first derivative? First derivative is a1. Second derivative is 2 into a2. F double dash of a is 2 into a2. Therefore, general fn is given by the formula. Fn is given by an. Okay. Fn is given by this formula. Fn of a factorial n. Okay. Next. We will do some consequences of theorem. Suppose there is f of z is analytic in a domain D and a is a point in some corner such that f and all the nth derivatives of a vanish at the particular point. Can we say anything about f of z? At that point it is 0. Can you say it is equal to 0 in the neighboring points? For that, we use the Taylor's theorem. Okay. This f of z is like this. Okay. Okay, I will do once again. Must have to- Okay, but anyhow, but by using the Taylor's expansion, we get that f of z equal to 0 in the neighborhood. But the theorem states that not only the neighborhood it is 0, it is 0 everywhere. So I collect, okay, I consider set of all points in the domain for which, at which f and all the nth derivatives vanish at that particular point. It is not empty, it is given already there. There may be a lot of points, collect all the points that is equal to A. A is not empty, but just now by using Taylor's expansion, we got that if A satisfies this property, then there is a small neighborhood in which for all the points z in the neighborhood, f and the nth derivative of f vanish at that particular z. Therefore, not only A belongs to this, if A belongs to this, there is a small neighborhood around A belonging to that A. Therefore, the given point A in capital A is an interior point of capital A. Therefore, A is an open set in D. What about the complement? Complement is D minus A. It is a point belongs to B if and only if either f of A is not equal to 0 or fn of A not equal to 0 for at least one n. Either f of A not equal to 0 or f dash of A not equal to 0 or f double dash of A not equal to 0, etc. Therefore, it belongs to the union. First set is f A not equal to 0, second set is f dash of A not equal to 0, all these things. And each set, the set of all points where f of A not equal to 0, it's a pre-image of complex plane minus 0. Therefore, it is an open set. Therefore, each one is open set. Union of open set is open. Therefore, B is also open. Therefore, both A and B are open. And B is disjoint from A because B is defined as D minus A. Therefore, my domain is the union of two disjoint open sets. But domain is an open connected set. Therefore, it cannot be represented as a union of two disjoint non-empty open sets. Therefore, one of the sets A and B should be non-empty. But A is not empty. Therefore, B should be non-empty. Since B is empty means D equal to whole thing. That means for all the points in D, this condition is satisfied. Therefore, F is identically 0 at every point. It is 0 or 0. So, if the theorem says that if the f is a function defined in the domain and A is a point somewhere in the domain where f vanishes at A, all the derivatives of f also vanish at A, then automatically f is 0, identically 0 throughout the domain. But the result is, okay, that is a statement. F of z is 1, then f is a point, then such a f of a, then f not equal to 0, then f of z is equal to 0. Is the above theorem true for the real valued function defined on the real line? Just now we proved the theorem for the complex analysis. With the real one, suppose f is a function defined on the real line, and A is a point such that f of A is 0, and f dash 0, f dash, that means in the real function, if f is analytic, f is differentiable, f double dash need not exist, but we had to assume that f n a exists for all the points. That means f is a c infinity function. It is differentiable any number of times. So assume that f is a differentiable function, c infinity function, and a is a point such that f of a is 0, and the nth derivative of a is also 0 for all n. Can we conclude that f is identically 0 on the real line? The answer is no. There are a lot of functions there. Okay. One example of the function is thus. Now consider the function e power okay, consider e power minus 1 by x square when x is greater than 0 and 0 elsewhere. It is a constant function up to 0 on the negative real axis, so it is 0 up to 0, and for then it goes up above the x-axis, and it is in between y equal to 0 and y equal to 1. The function is not 0, but at 0, all the derivatives are 0. Therefore, Taylor's expansion is not valid for the C infinity function. Therefore, this. So that is why we call that the function is analytic in the real line. If not only it is C infinity, it is C infinity and also Taylor's expansion is valid, then only we call that it is equal to this. Okay? Therefore, the answer for this is no. There are a lot of answers there. You can refer this example in the rooted real and complex one. That function is available for partition of unity. Then we will come to this next one. If f of x is identically 0 in a domain, then zeros are isolated. Just 1 minute, please. Just 1 minute. 1 minute. 1 minute. I will come. Just. Now f is defined. Okay. Okay. Just 1 minute. 1 minute. Hello. Hello. Let's get one of those. Square. Our domain D.
Yes, sir.
Okay. Okay. Sir.
Sir, okay. Yes.
Oh, okay. Okay. This is the domain D. Okay. Is A is a point such that f of A equal to 0. Okay. I want to prove that there is some small neighborhood around this point such that this is the only 0 for the function. That is, this 0 is isolated. Okay. Suppose, but the function is not identically 0. For that point A, what will happen? F of A is 0 already given. F dash of A may be 0, F double dash of may be 0, but not all the nth derivatives are 0. If all the nth derivatives are 0 and F of A is 0, then F should be identically 0. The function is not identically 0, it is given, and F of A is 0. Therefore, at least one of the nth derivative of F does not vanish at A. Choose the minimum M, I call that M, such that Fm of A is not equal to 0. So this is the first term in the Taylor's expansion, a non-zero term. All other previous terms will vanish. So this M, the least positive integer such that Fm of A is not equal to 0, is called the order of the 0 A at that point. Okay. So order exists. For every point, order exists. Therefore, what will happen? Taylor's expansion. Taylor's expansion is F of Z equal to first term is Fn of A by factorial M into Z minus A power M plus etc. etc. So I can remove this Z minus A to the power of M as a common factor for all these things. Then I get that Fm of 0 by factorial M plus etc. etc. If I substitute A in this bracket is therefore this equal to what will happen? Z minus A to the power of N into G of Z, analytic function. What is G of A? G of A, all other terms will vanish first except the first one, it is not equal to 0. So G of A is not equal to, at this point A, G of A is not equal to, G is analytic. Since it is not equal to the point, in some neighborhood, the function is not 0. So take that neighborhood. In that neighborhood, F of A is 0, but G of A is not 0. When F of Z is 0 means either Z minus A power M equal to 0 or G of Z is 0, but G of Z is never 0 here. And Z minus A power M is 0 only when Z equal to A. So A is the only 0 point for the function in this neighborhood. So if A is a 0 for the function, assuming that F is not identically 0, and A is a 0 for the function, then it gives a small neighborhood around that. It will not allow any other 0 to enter that. A is the only 0 of that. So we say that A is an isolated 0. So every 0 of a non-identically 0 function, F of is not equal to 0 identically, then every 0 of F is isolated. Okay? We need this theorem. Next report is PDF. Okay. Now using this result, we can prove the uniqueness of analytic function. Suppose there are two functions f and g, both of them analytic, defined in the domain D. And if there is a sequence Zn in D, such that distinct sequence, that is terms are distinct, Zn not equal to Zn, such that at every point of the sequence, both G and F give the same value, F of Zn equal to G of Zn for every n. We claim that F equal to G throughout the domain D. So there is uniqueness. If two functions are identical on a sequence, converging sequence converges to a point in the domain D, then if they identical on the sequence, then both of them are identical in the throat. This gives a uniqueness theorem. There are a lot of questions are asking in the CSIR exam based on this idea. Note that.
Check is it
sir, is it audible?
Video is.
Hello?
Sir,
Hello?
Yes, sir.
Video is okay?
Yes, sir.
Okay. Now, the most important point is the limit point Z0 should be in D. The limit point Z0 of sequence belongs to domain D, cannot be dropped from the statement. I will give an example to show that this is true afterwards. Okay. Next. Okay. Now we will give us a small problem. Okay. Using this uniqueness here. Using the uniqueness here. Okay. D is the open disk. Unit disk. Sorry. And D is the analytic function from the open disk to open disk. And the sequence one. F of 1 by n equal to 0 for all n, it is given that. What will happen that F identically 0 or F equal to 0 only when Z equal to 1 by n, n equal to 1, 2, 3. F of Z equal to half from some place, F is a non-constant. This is the objective type questions. What will be the answer? the sequence 1 by n belongs to the domain. It converges to what point? 1 by n converges to 0. That limit point belongs to D. Therefore, if two functions are identical on 1 by n, the two functions are same, identical throughout the domain. This function f is identical to 0 on 1 by n. And 1 by n tends to 0, which is a limit point in D. Therefore, by uniqueness of theorem, f is identically equal to 0. The answer A is the correct answer. Okay. This is a simple problem. Okay. Huh? Next.
Is it right or pick?
Okay.
Pen which?
Okay.
Pen. Inki. Listen.
அங்க எழுதல.
அதில் கொண்டு போ. அப்படியே கொண்டு போ.
Okay.
Is it right?
A.
Well, is.
Okay. A is right. அது மேல எழுதக்கூடாதோ? Okay. So f is identical to 0 is the correct answer. Next problem. F be slightly difficult problem. F be analytic function of the unit open disk. Which of the following is are true? More than one thing may be true. I don't know the answer. If for every positive integer n, 1 by n equal to 1 by n square, then f of z equal to z square for all z. That is one question. F of 1 minus 1 by n equal to 1 minus 1 square, then f of z equal to z square for all z. F cannot satisfy one condition, f cannot satisfy another condition. These things are given there. Which we will answer the question one by one. What about the first statement? Is it true or not? Second statement, true or not? What is the first statement? The sequence 1 by n is given. The sequence 1 by n is given. Answer is 1 by n square is given. The sequence 1 by n converges to which point? 0. That belongs to domain D. Therefore, if a converging sequence converges to a point in D, if the values of f are given, then you can find the uniquely. So f of 1 by n is 1 by n square. If you put z equal to 1 by n, what will happen? F of z equal to z square. So f is identically with z square. It is true here. So first answer is true. Okay.
அதை கொண்டே போடு.
Yeah.
இது கர்சர் இங்க வச்சிருக்கேன். ரெட் கலர். இது ஆன்சர் கரெக்ட். Which one is correct?
Correct. A is correct. A is correct. But what about B? B is a problem. What is the sequence given? 1 minus 1 by n. The sequence converges to which point as n tends to 0, converges to 1. But 1 is not in the domain D.
எழுதுமா?
எங்க போடலாம்? இங்க எழுதலாமா?
அப்படியே எழுது.
அங்க எழுதலாமா? வர போடணும்.
கொடுங்க.
இங்க போடுறேன்.
சின்ன போடுங்க. பேஜ்
இல்ல அதுக்கு என்ன எடுத்தா?
வரலாம்.
வைக்கணுமா?
இது வரா. நீங்க எதுவும் பண்ணணும். இருங்க.
சர்க்கிள். This is a unit circle I see there. What about the limit points? Limit points are half, 1 by 3, 1 by 4, 1 by 3 by 4, etc., etc. It goes on. What about limit point? Limit point is 1. The sequence 1 minus 1 by n tends to 1, but 1 is not in the domain D. Therefore, the uniqueness theorem will not be true here. F of z equal to z square is one function, but there are many other functions satisfy this property. Let us consider one more function. Let us consider a function g, such that g of 1 minus 1 by n equal to 0. But g is not identically 0. Can we consider this? We can consider this function by assuming the function g of 1 minus 1 by n equal to sin n pi. Suppose I assume g of 1 by n and g value at the point 1 by n equal to sin n pi. Then what will happen? At all these points, the values are equal to 0. But what is the connection? I put z equal to 1 minus 1 by n. Therefore, what is n? minus 1 by n equal to z minus 1. That is, n equal to 1 minus z by, sorry, 1 by 1 minus z. So this n, I can write this as, this is sine 1 by 1 minus z into pi. So when g of 1 minus 1 by n equal to this sine n pi. So g of z equal, if I put z, this value is z, then I get this value. So my function is g of z equal to sine pi by z minus, sorry, 1 minus z. What will happen when z equal to 1 minus n? Z equal to 1 minus 1 by n. 1 minus z is 1 by n. Therefore, sine n pi will get, sine n pi is 0. So we have constructed a function g which assumes 0 at each 1 minus 1 by n, where n equal to 1, n equal to 2, n equal to 3, etc. But the function is not a 0 function. The function is sine pi by 1 minus 0 function. Therefore, we have constructed a function which assumes 0 at these sequence points, but the function is not identically 0. So now consider the function z square, already given the z square I have proved, and the g of z. This is another function. Z square plus g of z is another function. This also satisfies the condition at every point 1 minus 1 by n, this value equal to 1 minus 1 by n square plus 0. So for z square plus g of z are same at every point and 1 minus 1 by n, but they are not identical function. So we get another function. So instead of this g of z, I can write g of z to the power of some k. This is also another function. Another function is, I can write z square, sorry.
Yeah.
Yeah.
இது பண்ணக்கூடாது, அது இங்கே லேப்டாப்கே வரக்கூடாது. இதுதான் இது எல்லாத்தையும்
அதை மட்டும் வச்சுக்கோ. ஓகே,
மீட் பண்ணிக்கலாம். வேணாக்கா.
Now, f of z equal to z square. This is one function. Now, I take g of z equal to z square into 1. But for that 1, I write this, instead of 1, I write this replaced by sine n pi by 1 minus z. This value is 0, therefore I write e power sine pi by 1 minus z. So my function g is g of z equal to z square into e power sine pi by 1 minus z. It's another function. Taking the values at every point 1 minus 1 by n is 1 by 1 minus n square. But therefore, we get lot of functions satisfying the same condition. This is because the limit point of the sequence is outside the domain D, not in the domain D. Uniqueness theorem says that if the limit point belongs to the D, automatically the function is unique. But it does not belong to D, it is not unique. How to construct a function? This is a method. Consider the sequence. At every point in the sequence, give the value 0. Give function g value. That is a g of g can be given as sine n pi. Find the correlation between the given point. Say here 1 minus 1 by n and there n pi. Put z equal to 1 minus 1 by n. Get the relation between n and z there and substitute n value there. I get the g of z, f of g of z. This is the method we are going to follow in all the problems like that. If the limit point is not on the domain D. Okay. Next. Okay. Now one more problem. F is a meromorphic function which is analytic at z equal to 0, satisfying the condition 1 by n, n by n by for all n. It is given. The meromorphic function is given. Analytic at z equal to 0. Okay. It may have poles and other things outside that. Analytic at 0 means in some neighborhood of 0, the function is analytic. The sequence is 1 by n is given. The sequence 1 by n belongs to this neighborhood after a certain stage, and it converges to 0, center of the neighborhood. Therefore, by uniqueness theorem, I have to find out the unique function, which satisfies the function f of 1 by n equal to n by 2n plus 1. But what is n by 2n plus 1? I substitute z equal to one. I substitute. Yeah. Okay. Okay. Correct. Okay. I substitute 1 by n equal to z. Okay. Then what is n? N equal to 1 by z. Substitute in the left hand side, right hand side. What is the right hand side? N by 2n plus 1 equal to n equal to 1 by z. Therefore, 1 by z by 2 by z plus 1, which is equal to 1 by 1 plus z plus 2. So the function is 1 by z plus 2. F of 1 by n is n into 1 by 2n plus 1. I substitute z equal to 1 by n. So what is z equal to 1 by n? What is the n value? N value is 1 by z. Substitute on the right hand side. Right side we get 1 by z by 2 by z plus 1, which is 1 by z plus 2. The function should be, what is the function now? Function is f of z equal to 1 by z plus 2. What about f of 0? F of 0 is 1 by 0 plus 2 is 1 by 2. First answer is correct. What about the function 1 by z plus 2? Is it analytic everywhere? No, it is not analytic everywhere, because the denominator is 0 and z equal to minus 2. So minus 2 is a pole. 2 is not a pole. It is given as 2 is a pole, but minus 2 is a pole. But so second answer is wrong. It has a simple pole at z equal to 0. No, it has a simple pole only when z equal to minus 2, not at 2. What is f of 2? Z equal to 2. When I substitute z equal to 1 by 2 plus 2 is 4. 1 by 4 is correct. No such manner. I have exhibited a function now. F of z equal to 1 by z plus 2 is a function which is analytic everywhere except the point z equal to minus 2. Therefore, it's a meromorphic function because it allows poles. Therefore, there is a function we have exhibited. Therefore, the fourth answer, no such meromorphic function exists, is a wrong answer. So, what about this problem? By using f of 1 by n equal to n by n plus 1, I have found out the function. By which way? I substitute z equal to 1 by n, find the relation between n and z, substitute the value of n on the right hand side. I guess the function is 1 by z plus 2. Then apply the condition f of 0 is half is right. F has a simple pole at 0 at z equal to 2 is wrong. F of 2 is 1 by 4 is correct. Fourth one is wrong. Okay. This is the method how to attack these type of problems. Definitely you are getting one question under this uniqueness problem. Okay. Same type of problem. This also net question. F is a meromorphic function. Analytic at z equal to 0. F of 1 by n equal to 2n by 3n plus 1. I want to find out the function. What is the function? 1 by n is a sequence converges to 0. 0 is in the here because it's analytic at 0 there. It is in the domain. Therefore, the function is unique. I have to substitute. Sorry. I have to substitute z equal. Oh, cursor. Z equal to 1 by n. Therefore, what is 1 by n? N equal to 1 by z. Substitute n equal to 1 by z on the right hand side. 2 by z by 3 by z plus 1. So answer is 2 by 3 plus z. So f is the value here. F value is 2 by 3 plus z. Okay. Now what is f of 0? Is 2 by 3 is correct. What about the simple pole? Simple pole is z plus 3 is 0. That is z equal to minus 3. That is not 2. Therefore, that is wrong. What about f of 3? F of 3 is 2 by 3 plus 3, 2 by 6. 1 by 3 is correct. No such function is wrong because I exhibited already. The function is 2 by 3 plus z. So function exists already. Therefore, the fourth one is wrong. Okay. Now, D is an open disk. The sequences are given 1 by n and 1 minus 1 by n. Two sequences are given. F of 1 by n equal to n by n plus 1. The sequence 1 by n tends to 0. So what is the value function? I can find the function here. அங்க போக மாட்டேங்குது.
கஷ்டம் எடுத்து நீங்களே போங்க அப்பதான் ப்ராக்டிஸ் ஆகும்.
அங்க போகணுமா?
போ இது பாருங்க இங்கே இப்படி மூவ் இப்படி மூவ் பண்ணுங்க அது மேலே வச்சு எடுத்து போங்க கிளிக் பண்ணுங்க
கிளிக் பண்ணுமா?
அப்படியே அதுலேயே ப்ரெஸ் பண்ணுங்க இப்போ எடுங்க.
Now what about
வரல இது பாருங்க அப்படி வரணும் பாயிண்ட் எடுத்துங்களா
அந்த
பண்ணுங்க
z equal to 1 by n. Therefore, n equal to 1 by z. Substitute there, I get 1 by z by 1 by z plus 1. Therefore, this is 1 by z plus 1. The answer should be 1 by z plus 1. Okay. But if I take this other one, minus 1 by n equal to z, then I get the value minus 1 by, okay, minus 1 by minus 1 plus z. The function is 1 by z minus 1. But if I consider the sequence 1 by n, I get the answer 1 by z plus 1. If I consider the sequence minus 1 by n, I get the answer 1 by z minus 1. There are two different answers, but a uniqueness theorem is not possible. Therefore, there is no such function satisfying this condition. It satisfies two conditions now. F of 1 by n equal to n by n plus 1. If I use that, the function should be 1 by z plus 1. But instead of that, if I choose the second sequence minus 1 by n, the function should be 1 by z minus 1. These two functions are different functions because one is 1 by z plus 1, another is 1 by z minus 1. These two are different functions. Therefore, by uniqueness theorem, it is not possible to have a different function. Therefore, there is no such function satisfying both the conditions here. Okay. Now, this is a very good problem. S is a disk. What is the radius of the disk? Is 3 radius and a C to be an analytic function such that the sequence value is given at some points. What is the value here? This is assume that this is a circle with the radius 3 and the sequence points are given as, okay, 1 point, 1 point, another point, another point. The sequence tends to this. What is that? 1 plus I into root 2 by n converges to, as n tends to infinity, it tends to 1. So the sequence tends to 1. 1 belongs to domain. Yes. Therefore, there is uniqueness function. I want to find out the function. How to find the function? The sequence f of 1 minus, this is given as f of 1 minus I root 2 by n equal to minus 2 by n square. Therefore, I have to take z equal to 1 plus I root 2 by n. Therefore, 1 by n equal to, what will happen? 1 by n equal to z minus 1 by I into root 2. Now, what is the right hand side? Right hand side is minus 2 by n square. 1 by n square. 1 by n square is, what will happen? Z minus I whole square. Z minus 1 whole square. Sorry. Z minus 1 whole square by I square is minus 1, minus 2. Therefore, minus 2 get cancelled. Therefore, function should be equal to z minus 1 whole square. Verify. The function is z minus 1 whole square. What is the value at 1 plus I root 2 by n? Is it equal to minus 2 by n square? Z minus 1 is I root 2 by n whole square is minus 2 by n square is correct. So, my required function is z minus 1 whole square. So, f of z is, what is the f of z? F of z equal to z minus 1 whole square. Now, what yes, asked to find out the value of some point. in the domain root 2. So substitute the value f of root 2, f of root 2 equal to root 2 minus 1 whole square, because the function is z minus 1 whole square, of root 2 minus 1 whole square equal to 4 minus 2 root 2 plus 1. Okay, okay, correct. No, this is 2. Root 2 square is 2. 2 minus 2 root 2 plus 1, which is equal to 3 minus 2 root 2. So answer is 3 minus root 2 is the first one is the correct answer. All other answers are wrong. They are just a combination. 3 minus root 2 plus 3 plus root 2. 2 minus root 2 is a permutation combination, but one answer is correct. What is that? Now, I think it is very clear for you now. The sequence is given, the values are also given, the sequence converges. By this data, I can find the value of the function. What is here? 1 minus I root 2 by n equal to, substitute z. Then I can find a n equal to, what is 1 by n? 1 by n equal to, I have followed something else, and substitute in the right hand side. Substitute in the right hand side for n, substitute the value, I get the z value. So I get if z f of z value which is valid throughout the domain mod z Sn3, and root 2 is a point there, substitute the root 2 value, find the value of that. Now another problem, does there exist another function on the region domain D such that 1 by n equal to minus 1 by n square, where n equal to 3, 4, etc. Okay. There are two regions are given. The regions is different. If the region D is a disk, mod is less than 1, what will happen? If it is outside, what will happen? The first region is, this is the region. Okay, see, 0 is the point. What is the sequence? Sequence 1 by n tends to 0. So 0 belongs to domain. Therefore, if at all there is a function, it should be unique. But what is f of 1 by 2 equal to plus 1? F of 1 by 3 equal to minus 1. F of 1 by 4 equal to 1. Okay, the function takes 1 and minus 1, 1 minus 1 here. If you consider the sequence half, 1 by 4, 1 by 6, 1 by 8, 1 by 2n sequence consisting of 1 by 2n, the values are 1, 1, 1, 1. Therefore, function should be equal to 1. But if you take odd integers, f of 1 by 3, f of 1 by 5, 1 of 1 by, all the values are equal to minus 1. Therefore, this suggests that function should be equal to minus 1. At one side, the function should be equal to 1. At the same time, it should also equal to minus 1 because it satisfies 1 by 3, 1 by 5, all these are minus 1. It is not possible to have one value or minus 1 at every point. Therefore, the first one is wrong. This wrong because the sequence 1 by n tends to 0, and we get two different values. Sequence tends to two different values function. Therefore, it's not true. What about second one? Second one is also disk with center is 1. And the limit point 0 is not on the board. Okay, the sequence 1 by n tends to a point not on this set. It tends to a boundary point. Therefore, the theorem is not applicable here. There may be a function. Okay, now I have to consider the value. Just now, as I said that, okay, 1 by 2, 1 by 4, 1 by 6, all values gives the value 1. 1 by 3, 1 by 5, 1 by 7, all gives minus 1. So I want to take a function which takes the value here at 1, and value here is minus 1. So it is better to have the function, sine function once again. Sine, where is the function? Okay. I consider the sine. Okay. What about 2n? Okay, 2 by n. What is n? N equal to 1. So sine value is not minus 1 plus 1. Okay, I like this. Sine, okay, pi by 2. Sine pi by t is 1, sine 3 by 2 is that. Therefore, I write this n, where n not equal to 2, n not equal to 4 to the power,
0.
4 put a 0. I want to take a value here, therefore I have to get a pi by 2, 2n plus 1. Can I put a 2n?
Order.
Huh?
Order. Even with the 0.
Ama.
Order. All odd numbers.
Sine 2n plus 1
Into pi.
into pi by 2. When n equal to 1, 3 pi by 2. N equal to 2,
5 pi.
answer is yes. So I take sine 2n plus 1 by 2. It takes a value 1 minus 1, 1 minus 1, etc.
Possibly.
Okay. So I have to consider this 1 by n equal to z. So z equal to 1 by n. 1 by n equal to z is z equal to 1 by n. Therefore, n equal to 1 by z. I have to substitute n equal to 1 by z here. The function is what is the function? Function is sine. Okay.
Previous.
Okay. Huh?
Previous.
Previous stage, yeah.
Yeah.
This one. Okay. Got it, right? Okay. Function is sine 2n plus 1 pi by 2. But n equal to 1 by z. Therefore, what will happen? 2z by z into pi by 2. Okay. 2n 2 by z plus 1. Considering this, 2n plus z by z is 2. Okay. If I use this function, we get it. So for the second one, because 1 by n tells you a limit is not in the domain D, I am able to find out the function. So not only sequence depending upon D, the limit point belongs to D or not D. Belongs to D means we get a contradiction because we get two different values, but D is outside, the limit point is outside, means okay. Therefore, the second one is correct. Second one is correct, first one is wrong. For the second one, function is sine 2n plus 1 pi by 2, where n equal to 1 by n. Substitute, I get the answer. Okay. Is it clear? Very clear? Hello? 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 Hello?
Yes, sir. Yes,
Okay,
sir.
okay.
Yes, sir. Clear.
Okay, right. Okay. Okay. Now we get this is an important problem. F of z is an entire function. An entire function means analytic throughout the complex plane. F is a real on the real axis. That is f of z bar. That is equal to இது மேல அது பார் f of z பாருக்கு அந்த பார் அங்க வந்துக்கல அது மேல ஓகே எங்க இருக்கு இந்த பார் this is f of z bar equal to f of z for early set. Okay, how to prove this? I will prove this like this. Now consider the real line. When z is real, what is f of okay. Okay. When okay, I consider when z is real, What will happen? Z bar equal to Z. What is f of Z bar? It's also f of Z. F of Z is real, it is given. Therefore, f of Z bar equal to f of Z. Therefore, f of Z equal to f of Z bar is true on the real line. In the real line, I can take a sequence which converts to real point. Therefore, by uniqueness theorem, it is identical throughout. F of Z bar equal to f of Z throughout. Okay. So first one is correct. Now second one is f of Z is real on the real axis and purely imaginary on the imaginary axis. Then f is an odd function. Okay.
No. Extra.
Or extra.
Page.
Page. Seri விட்டுங்க. இதிலே போட்டுறேன். Okay. Okay. Now what is, so I have proved that f of Z bar equal to f of Z because f is real on f of Z. Now what is given when Z, f of Z is real, if Z is some IB, purely imaginary. So if Z is purely imaginary, then what about Z bar? Z bar is minus Z. For example, I4, what is the conjugate of that is minus I4. So this, so f of minus Z equal to f of minus Z bar because of this problem. Okay, because of this, I get it. This is equal to f of minus Z conjugate. Since minus Z is a purely imaginary, minus Z is also purely imaginary. Therefore, that conjugate is a real number. That is also therefore equal to f of Z minus bar. Okay. Oh no. This is a minus Z here. F of minus Z equal to minus Z bar is plus Z bar. F of Z is purely imaginary. Therefore, I get f of Z. So if it is purely imaginary, I got that f of minus Z equal to minus of f of Z. That means f is an odd function. Okay. Next. Previous one. Previous.
Slide. Yeah.
அதுக்கப்புறம் இன்னொன்று இருக்கும். இது அடுத்தது விட்டு போச்சு. வேணாம். சரி,
டிஸ்கஸ் பண்ணிட்டு
இல்ல அது பண்ணல. இன்னும் நோட்டு போய் முன்னாடி விட்டுருச்சு.
கரெக்டாக தான் போயிட்டு
கரெக்டாக இருக்கா?
ஓகே டிஸ்கஸ் நெக்ஸ்ட் வந்து எக்ஸ்பிளனேஷன்.
ஓகே,
இதுக்கப்புறம் இப்போ டிஸ்கஸ் பண்ணுவோம்.
Okay. Now, consider the other problem. F is an entire function. A is greater than 0 be a real number. Assume that f of Z is real whenever Z is a real. What is given that f of Z is real whenever Z is real, or imaginary part is this. That means what will happen? Okay. This is the point A. Consider this. F is real whenever f of Z is real whenever Z belongs to this or Z belongs to this. Okay. Now we want to prove that f of Z minus A equal to this. Because f is real whenever Z is here, I get f of Z bar equal to f of Z. Okay. Now I have to consider Z plus IA. When Z is real, what is f of Z plus IA? That is also real. Because the imaginary part is A, therefore Z is a real number, therefore Z plus IA imaginary part is A only, therefore this is equal to real number, but this is also equal to Z plus IA bar into bar because of the condition. This is the f of Z minus IA bar, but this is a real number, therefore this is also a real number, therefore I need not consider the conjugate same thing else. So I get the first answer. The first one, I get the first answer. This is, I have proved this. Simple. F of Z plus IA, when Z is a real, when Z is a real, then f of Z plus IA equal to f of Z plus IA bar into bar equal to f of Z minus IA bar. F of Z minus IA is real, therefore I get it is equal to this. So these two functions, this function and these functions, are identical on the real line, therefore identical throughout by uniqueness theorem. What about the second one? Second one is f of z plus 2ia. I can write this as f of z plus ia plus ia. Consider z plus ia as 1z. Therefore, this is what will happen. F of z plus ia minus ia because of this first property. So this ia get cancelled. I get equal to f of z. So second one is also true. Third one is wrong. I want to give one example. What is given? Is it true for every such entire function? If f is an entire function satisfies the condition, is it true? No. I have to give an example of an entire function for which the third one is wrong. Okay? F of z plus ia equal to f of z is wrong. I have to give that picture. Okay. Oh.
Next,
Next slide one.
blank.
Blank. Okay. That one, huh? Okay. I take a equal to pi, I pi. Pi a equal to pi, therefore the point is I pi, imaginary part is pi. Okay. So what about f of z plus ia equal to f of z plus I pi? I take a function f as e power z. It is an entire function. Substitute here, what will happen? E power z plus ia equal to e power z plus I pi equal to minus e power z, because e power I pi is minus 1. So this is not equal to f of z. Okay, if I take a point z here, I consider the point z plus ia here, both will not have the same value. This value is minus times of that. So the third one is not true, because I have given the function f of z equal to e power z, for which the other conditions are right. If it's 2a, what will happen? F of z plus e power I. Okay, okay, this is, we get the answer for that. Next.
Sorry.
That's the one.
You would explain.
Wait. Thus, there exists a function which is analytic in the open disk, satisfying each. 1 by n equal to 0 for n odd positive integer, equal to 1 on even positive integer. So what will happen? 1 by 3, at 1 by 3, 1 by 5, 1 by 7, answer is 0. The 1 by n tends to 0, limit point tends to 0. 0 belongs to the domain. Therefore, f of 1 by 3, f of 1 by 5, all 0 means suggests that the function should be a 0 function. But at the same time, f of 1 by 2 equal to f of 1 by 4 equal to f of 1 by 6 equal to 1. So this suggests that f should be 1 at all places. By considering one case, f of z equal to 0 for all z. By another way of taking that 1 by 2n only 4, and I get the answer is 1. It is contradiction, therefore there is no. Okay. The first one is wrong, because I get 0 one side, 0 1 another side. What about the next one? 1 by n tends to 0 when n is odd, and 1 by n. When n equal to odd, f of 1 by 3, 1 by 5, 1 by 7, at all places is 0. No problem. What is okay? Therefore, the function should be, what will happen? The function should be 0 function. But at 1 by n, the function value is 1 by n, it is not 0 function, therefore it is also not true. F of 1 by n equal to n by n plus 1, function is possible, because substitute z equal to 1 by n. When we take z equal to 1 by n, what is n? 1 by z. Substitute the value n equal to 1 by z on the right hand side. 1 by z by 1 by z plus 1 is 1 by z plus 1. 1 by z plus 1 is a value. Okay, when 1 by n equal to this value is true. The second one, the fourth one is also wrong. 1 by 4, 1 by 5, 1 by 6 gives the value 1 by give the value z square. F of z equal to z square. If I take 1 by 2, 1 by 5, 1 by 7, 1 by 6, the sequence converts to 0. This 1 by n, the answer is 1 by n square, z square. Therefore, f of z should be z square. Whereas if you consider the second one, f of minus z equal to z square. So what will happen? That is not possible. Okay? Because minus 1 by z square is also true. Oh, okay, this is also f of minus 1 square is also, therefore the function should be equal to, the function is there. The value is z square, it's a function. For 1 by n value is n square, or minus 1 by n also value is n by square. F of z equal to z square is a function, satisfies this property, it is true there. What about the next one? Next one, similarly we have proved already. 1 minus 1 by n, the limit tends to 1, which is not in the boundary. Therefore, I can substitute the minus 1 by n equal to sine, okay, sine n pi, like that. Sine n pi by 2 like that. I had considered, we already considered that. The same way we can consider the next one also. Okay, these are simple problems. I can give this as exercise problem for the parents. Find out the zeros. The z cube into sine z. Z cube is 0 when z equal to 0. Sine z is 0 when z equal to 0, or pi, 2 pi, 3 pi, etc. So what about the zeros of sine z? 0, n pi is a 0. Sine n pi is 0 for all n plus or minus 1 plus or minus 2 including 0. For 0, z cube is also 0, is 3 times. I get one more 0 from when we substitute z equal to 0, I get 1. Therefore, the order is 4 when z equal to 0. For all other zeros, for example, pi, 2 pi, 3 pi, 4 pi, I get 0 only from sine z, not from z cube. So I get order is 1. So work it out. This problem I give it an exercise problem. Next class you can expect you can give the answer for these problems. Okay. Okay. This is another problem. F is a function. Okay. The domain F is a function. There is another domain here. For that G is a function. So I get the composition function. So I get the composition function h equal to gf. Suppose z naught is a point here. Its image is w naught. It is a 0 for the function g. G has a 0 at order m. Then what will happen? Is it a 0 for the composition function h? Like that, the question is that. Think it over the question. This answer is very simple. You can prove this theorem. Just substituting the power 1. Okay. I will answer this question in the next class. Now we get the Cauchy estimate. Therefore, we set a domain. Therefore, we set is analytic in a domain D. A is a point, and the domain contains a circular disk, closed circular disk with a radius r, center A in D. And on the circle, the maximum value of f of z is mod f of z is m. The bounded function, its value is m there. Okay. Then Cauchy's estimate gives that modulus of nth derivative at a, fn of a is less than equal to factorial n into m by r power n. For the moment, we can assume this result, or I can prove this now. There is a formula fn of z equal to, okay, factorial n by 2 pi I integration over c setting f of psi by psi minus z to the power of n plus 1 dz. Okay. Now I get the modulus on both sides. Modulus is less than equal to factorial n by 2 pi. This is mod f of z, maximum value is m there, by r power n plus 1. Length of the circle is 2 pi r this r and 1r get cancelled. This 2 pi and 2 pi get cancelled. So I get factorial n m by r power n. That is the right hand side. So mod f of fn of a is less than or equal to this. This estimate that when n equal to 1, I get the second one. That is Cauchy's estimate. We use this problem. There are plenty of problems they are asking. At least one question in each one using these two formulas. I will come to that problem. Okay, if f is a function bounded on entire function, then it reduces a constant. It is a Liouville's famous theorem. F is a bounded entire function, then reduces to constant. Okay, use that. What is f dash of a? F dash of z. Modulus f dash of z is equal to m by r. But f is bounded. I take that bound as m. This is true for all. Okay. So if we draw a circle here with z is a point and radius is r, this value is m by r. But I can increase the radius. I can go on because the function is analytic, entire function. So I can take r as a large. As r increases, the denominator increases. Therefore, this tends to 0 as r tends to infinity. So this shows that f dash of z equal to 0 here. So I get that f dash of z equal to 0 for all z belonging to the complex plane. The derivative 0 means it should be a constant. This is a famous Liouville's theorem, a simple proof based on the Cauchy's estimate for the first derivative f dash of z. The problems using this. Finish your energy. Okay. Okay. Next open side. Open. Time ago.
12:10.
Huh?
12:10.
12:10.
12:10.
Yes. Now consider nature.
No.
Let f be an entire function. Okay, it is analytic everywhere, such that f of z is not real for all z. The function value, there is no z such that f of z lies on this. What can you say for f of z? So values for any z here, value is f of z may be here or maybe here. So I can divide this set into two parts, where A, for which f of z in the upper half plane, for other parts B, where f of z belong to this lower part. So my complex plane has divided into two parts, A and B, where these points, imaginary part of f of z is positive, for this part, imaginary part is negative. Both these things are open set, this is also open set. Fourth complex plane is the disjoint union of two open sets, but the complex plane is connected. Therefore, one of them is empty. Either B is empty or A is empty. This shows that f of z completely lies in the upper half or it lies in the lower half. If f avoids a real line, f of z is not real for any z, the f value should be in the above or f value should be in the lower half plane. Let us consider this case. F of z belongs to the upper half plane. Then the point minus I is not in the image. So mod f of z minus I, that plus I. What is the distance? The distance is at least greater than 1, therefore greater than or equal to 1 for all z. So mod f of z plus I is greater than 1. Therefore, consider the function 1 by f of z plus I. It is a bounded function. What is the modulus of this? Mod f of z plus I is greater than equal to 1. Therefore, this modulus, okay, this modulus is less than equal to 1. Therefore, this function is a bounded entire function. Therefore, by Liouville's theorem, it should be a constant. That is, f of z plus I is a constant. Therefore, f of z is a constant function. So, if an entire function avoids the real line, the image, no image is on the real line, then the function is a constant function. This gives a nice idea because the point -1 is not in the image. F is an entire function. The image set is here. The minus I is outside this. Not only that, I can find out a small circle around this such that this neighborhood will have empty intersection with this. This shows that this point is not a limit point of the image. So if there is a point which is not the limit point of the image, then f should be a constant. That means if a non-constant entire function should be dense in the complex plane. Okay?
Next.
Okay. திருப்பி வைக்கிறமாங்க. Now consider f is analytic and f of z bar is not equal to c given. Therefore, I can find a point A here, which is not the limit point of the image set. Therefore, I can find a small circular disk which will not intersect this. What is the radius of this delta? So this shows that mod f of z minus a is greater than or equal to delta for all z. Therefore, 1 by f of z minus a is less than or equal to 1 by delta for all z. That means this function is a bounded entire function. Therefore, 1 by f of z minus a is a constant function. Since 1 by f of z minus a is a constant, f of z minus a is also constant. Therefore, f of z is a constant. So, if f is an entire function which is not a constant function, then the image should be closure of the image should be equal to entire complex plane. Okay, but there is another theorem says that, which is better than this. Picard's theorem says that what about the image of f is completely whole thing, or it can avoid only one point. So f of z equal to entire either c or c minus a singleton is a notch. It can avoid only one point. Image set can avoid only one point. That is called Picard's theorem, little Picard's theorem. If f is a non-constant entire function, constant entire function takes only one point as image. It avoids anything else. If it is not a constant but entire function, the image should be either the entire complex plane or it is entire complex plane except one exceptional point is a not. For example, consider f of z equal to e power z. What about e power z? Image is everywhere except 0. E power z is not 0 for any z. So this is not equal to 0. Except 0, all other values are taken for suitable z here. Therefore, this is an example of an entire function which avoids a single point. If a non-constant function avoids a single point, it should avoid only one single point. No, nothing else. That theorem is called little Picard theorem. This helps us to answer many questions. Please, I will Okay, now the question is this. Now f is a entire function. F is entire function. Suppose the image is in between. Image is in between the strip what can you say? F is a constant function because the image in the strip, it avoids this point, this point, this point, this point, etc. It avoids more than one point, therefore f should be a constant function. Similarly, f is an entire function if the image is here, then also f is a constant function. If the image is in the upper half plane and this point and these things are omitted in the image, then it is a constant function. So they are asking like this, using just a little, you do not want the proof of the Picard's theorem, but just to have the statement of the Picard's theorem. Little Picard's theorem says that if f is a non-constant entire function, its image is either C, entire C, or C minus a single point. It can omit at the most a single point. Okay, if the entire function avoids more than one point, then it should be a constant. They are asking questions like this. Just using this, remembering this, you can put the tick mark, etc. Okay. Are you able to hear, sir? Hello? Hello? Hello?
Oh, yes, sir. Yes,
Oh.
sir. Yes, sir.
Oh, can I stop at this point? If
Okay,
there are any questions there, we can answer this. Okay, because this is
Okay.
my first trial in online.
Okay, sir.
Problem.
Okay, sir. No,
Okay.
no problem.
Face.
Hello.
Ah, yeah, sir.
Okay. Yes, please.
Ah, okay, sir.
Ah. Any questions from the audience? Hello.
Ah, yes, sir.
Any questions?
Sir, 1 minute, sir.
Okay.
How do you give it?
Sir, from audience, no questions, sir, now.
Okay.
Till now, no questions, sir.
Okay. Okay.
Okay. Okay.
Okay. Thank you very much. Hello.
I need. Ah, yes, sir.
Oh, yes, please. Yes.
Yes. I need to multiply. I need to multiply thank you word 1,000 times to match it with your effort, sir. We wish to express our gratitude to our resource persons for being with us on this event. Your presence and gentle words are a source of encouragement for all of us, sir. Thank you so much, sir.
Thank you. Thank you very much. Thank you. Thank you very much.
Thank you so much, sir.
Thank you. Thank you.
Limitations live only in our minds, but if we use of our imagination, our possibilities become limitless. My sincere thanks to our HOD sir, Professor R. Venkatramanan, for organizing this C4 workshop. With happy fulfill mode, we move to the end of the workshop. Our next section is 17th October at 6 p.m. Thank you, one and all.